on this. Okay, so so everyone, I have gone ahead and started recording for this session. So just for whoever is here, just so you know, please make sure that you're on mute, and this session is being recorded at this time, and we'll sort out how best to get it out for those that are unable to attend.
Shall I start?
Yes, please go ahead to start at this point.
Okay. So it's a real pleasure, and thank you very much for inviting me to this IEEE Distinguished Lecture. I have been to Florida a few times, but I haven't lived there, but I really like Florida. And so this is a talk on how to connect the space access to the internet. So if we look at, try to get this thing away from the. So if we look at the satellites over terrestrial networks, there are a number of advantages of satellites over the networks we are used to, like the Wi-Fi and the 5G and Bluetooth and all sorts of networks we are used to on Earth. Satellites is not a network which is used by everybody. It's not a commodity stuff. You can't buy, you don't get it in the internet, you don't get it in the Walmart like other networks you get. But the advantages are it is a ubiquitous network. It has ubiquitous coverage. It covers all the whole world, in contrast to terrestrial networks, which cover only small regions, like Wi-Fi cover a house, 5G covers cities and highways, but it doesn't go to mountains, it doesn't go to ocean. Satellite coverage is ubiquitous and it's very reliable. It doesn't break down as often as other networks. And the coverage in remote areas and underserved regions are especially attractive. Like it covers places like forest, like ocean. When you're up in the sky, when you're flying in the aircraft, that's where you need satellite coverage because it covers everywhere. It's also used for places like war scenario where you cannot set up a network. You are in territory, enemy zone. So you really need something like a satellite network which gives you coverage from the sky. And the good advantage is it permits the use of a single platform as compared to a patchwork of terrestrial networks. Like when we're at home, we use Wi-Fi. When we are on the road, we use 5G for near communication. We use Wi-Fi, which is okay. So these are all optimized for different tasks. This is a network which has which is a single platform. Now, if we look at the Internet of Things over satellite growth, you will see that the growth is sort of linear as expected. Terrestrial networks have exponential growth and exponential fall as well, but satellite networks have more stable growth, and you can see that is going to grow over time. If you look at a satellite, what is inside a satellite? The satellites have two functions. One is looking up to the sky to explore the space. So they have got equipment like telescopes and I don't know what other scientific instruments they have to discover space. The other type of satellites look down to Earth and they look at things like disasters, things like vegetation, precipitation, all sorts of things they look at. And depending on what your mission is, do you want to look down into Earth or do you want to look up into the sky? You use different types of instruments on a satellite, and this is called the payload. And this is an example of a Juno satellite and the payload. You can see there are, excuse me, there are a lot of scientific instruments. There are radiometers, there are magnetometers, there are oral distribution experiment stuff, ultraviolet spectrograph, all sorts of equipment are there. The equipment up on the satellites are not that important for us to understand. It's important for us to understand that these equipment are sensors. They collect information and they relay them down to Earth for scientists to analyze. Now, the current state of the art is these are downloaded to Earth using dedicated lines. So the objective is, can we connect these devices to the internet like we have connected the cell phone, like we have connected the refrigerator, like we have connected the cars, and everything we are connecting to internet. So can we also connect these scientific instruments which are up in the sky on the satellites to the terrestrial internet? That is the objective. And the answer is, of course, yes, but there are a lot of challenges to solve. But it is possible to connect these onboard science equipment to the terrestrial internet, which we are used to. Now, if we look at satellites, we have to see what is the challenge there. So these spacecrafts have IP addressable payloads, and they could be sensors, they could be radars, telescopes, and they could be equipment observing the weather. There could be fire detection equipment up there on the sky. And these are sort of, in general sense, these could be called Internet of Things, because whatever you connect to the internet becomes Internet of Things, and it sends data to the internet. However, these things are something special in that they're mobile, and they are connected in a LAN on a spacecraft, which is also moving. So not only is the LAN moving, the devices are moving, and everything is moving up in space. So if you look at the satellites which are up in the sky, there are 3 different types. One is the geostationary satellite, which is stationary with respect to ground. So these satellites rotate at the same speed as the Earth. And there are other satellites which are closer to Earth, like the low Earth orbiting and the medium Earth orbiting. The low Earth orbiting is the closest to the Earth, and the medium Earth orbiting is somewhere in between the LEO and the GEO. And you can see the distances. The GEO are very high up, 35,000 kilometers. The LEO are much closer, 300 kilometers to 1,000 kilometers. They're very close to Earth. The closer to Earth, the lower the power you need to communicate with the satellite. That's one big advantage. Second big advantage is the communication delay. If you are to communicate via GEO satellites in real time, I mean, that 35,000 miles will take up almost a quarter of a second one-way propagation delay. Round trip delay. So if you want to do real-time stuff, then GEO is not very suitable. Let's say voice, interactive voice. So you have to go to satellites like LEO satellites. So in this talk, we are going to focus on LEO satellites, because most of the satellites which carry these Earth observing equipment, they're actually LEO satellites. So when we connect these satellites down to the terrestrial network, a big issue is the mobility management. How do we manage the mobility of these satellites which are actually rotating around the Earth? So let me give you some example of handoffs in satellite IP networks. Whenever there is a mobility, there is a handoff. We are used to this handoff issue. There are 2 things in mobile networks. One is handoff, another is reconnecting to the new base station wherever we are. So if you look at the handoff, there are 2 different types of handoff, link layer handoff, and also the network layer handoff. And I'm going to discuss those 3 which are highlighted in satellite handoff. And for the network layer, I'm going to look at the satellite as being used as a router, and when the satellite is used as a mobile host, and the sort of handoffs they encounter, just to give you an idea about the sort of mobility we encounter in space and the challenges from there. So in this particular case, there is a satellite which is connected to the ground station, and the satellite moves away, and the new satellite has to connect to the ground station. So this is ground station is handing off between the satellites. So this is an inter-satellite handoff. This is similar to the inter-switch handoff in the case of terrestrial mobile networks. And if you look at network layer handoff, and in this particular case, there is a scientist who is accessing the internet from a place like a desert where she has no access to the internet. So she accesses the satellite, and the satellite relays the connection or the packets down to ground station, from where she can access the internet. But these are LEO satellites, which means they are rotating around the Earth. And after some time, these satellites are going to move away, and a new satellite will come over that person. So the person is under the footprint of a new satellite, which means that we have to hand off the connection which she was having from the previous satellite to the new satellite. So here is an example of handoff. one thing we have to understand is, in this particular case, the satellites are acting as an IP routing device. The satellite is just routing the packets from the user to the ground station. In this particular case, there is no onboard device. It's just relaying the data. Now, satellites are allocated different IP prefix at different regions, because when they connect to the ground station, they have to get a new IP address. And of course, when the new satellite comes over, the person's IP address has to be changed as well. So the host needs to maintain continuous connection with the remote computer. That is what our objective is. Here is an example of a network layer handoff. And I'm going to discuss a second case where the satellite is used as a mobile host. In this particular case, the satellite, the onboard equipment on the satellite, they are collecting data and they are downloading the data through the ground station to the scientist, for example, to analyze the data. So in this particular case, we are talking about this satellite having onboard equipment collecting data, in contrast to the previous one, where the satellite did not have any onboard equipment to collect data. So here again, the satellite is downloading the data through the ground station, but since we are considering LEO satellites, the satellite is going to move away and get connected to a different ground station. We know that IP addresses are geographically tied. That means the IP address in Oklahoma is different from the IP address in Florida, which is different from IP address in France. As soon as this ground station, as soon as the satellite hands off between two ground stations, this satellite has to obtain a new IP address because the new ground station is geographically located in a different place. And having a new IP address, the communication has to be reestablished. Now we are talking about seamless communication so that the user is not aware of this handoff. That is what we are talking about. So what I was just showing you is there are a lot of handoffs going on in space, and his handoff management is a big issue whenever we have mobility, especially in satellite environment where the propagation delay is large, the error is large. Sometimes you have different coverage in different areas. So it's a real challenge to manage these handoffs. So I'm going to discuss the rest of the talk on mobility management. How do you do mobility management when these satellites are moving around, these devices are moving around? So the question is, how does the US postal system do mobility management? So there's a form, if you go to USPS and say that I have moved from one address to another address, you fill in this form and you provide your previous address in New York, give it to the post office in New York, and also write down your new address. So the post office in New York will not deliver the address to 95 Morton Street. It will intercept the delivery of that of those packets or mails, and those mails will be delivered to a different post office whose address is given below. That is how mobility management is done in the US postal system. The fundamental principle is mail forwarding. Whenever a mail comes into an old address, it is being forwarded to a new address. That is a fundamental principle of the US postal system doing mobility management, because you're mobile, you're moving from address to address. Based on this concept, the IETF developed a protocol called mobile IP. It is based on very similar concept like the US postal system. We can see that there's a correspondent node which sends data to a mobile host. The mobile host was initially in the home network, and in the home network, there is a home agent. It was connected to the home agent. But when it moved to a foreign network or a visiting network, it obtained a new IP address from the foreign agent, because we know that whenever you move to a new router or new location, you have to get a new IP address. The first step for the mobile host is to send a location update to the home agent saying that I have moved to a different network where I'm visiting. In response to that, the home agent will forward all packets to the foreign agent, and the foreign agent is going to send or forward the packets to the mobile host. So sending the packets from the home agent to the foreign agent, they are encapsulated because they are just sent from the home agent to the foreign agent. So it establishes a tunnel where the packets are actually encapsulated. So this mechanism is exactly the same as a US postal system, that you have moved from your home agent to a foreign agent, and your packets coming from the correspondent node to the home agent are being forwarded to the foreign agent. And when you're doing the location update, basically that is filling in the form you do at the post office saying that I have moved. Now, a few drawbacks of the base mobile IP, and I must stress that this is base mobile IP because a lot of modifications have been done since mobile IP was introduced. Number one, it needs modification to the internet infrastructure in the sense that if you want to do mobile IP, there needs to be a home agent and a foreign agent. In the standard internet infrastructure, those home agents and foreign agents are not there. These are required by the base mobile IP protocol, by the standard. So if I want to do a mobile IP between my university and the wherever I'm traveling, if I go and tell the university that I'm going to move, can you start a home agent? Highly likely they will say, no, we can't do that because it's not too many people need it. And so modification to the internet infrastructure is always difficult. Those of you who have followed the progress of the internet protocols, there are a lot of very nice protocols which have been developed, which require change in the internet infrastructure. And you will see that most of them have failed because changing the internet infrastructure is extremely difficult for two reasons. The internet is so big. Number two is no one owns the internet. The parts of the internet are owned by different people. So there is no, unless there's a big motivation or there's a big money involved, changing the internet infrastructure, any protocol which needs change to the internet infrastructure is extremely difficult and highly likely to not succeed. And we have seen lots of protocols like DiffServ and all sorts of things to ensure quality of service. And there are lots of other which have not actually succeeded. But if you look at the protocols which require only changes at the edge, they are highly likely to succeed. Like the NAT is highly successful because you just use it at the edge of the network. The other issue with the base mobile IP is there's a big handoff latency when you are handing off between the home agent and the foreign agent. And while doing this handoff, if it takes too long, packets coming from the correspondent node are highly likely to be lost. Some of them may be buffered, but when the buffer is full, it's going to overflow. Number one. Number two, it's very difficult to run interactive services when there is high handoff latency. The routing path is very inefficient. Packets come from the correspondent node to the home agent and being forwarded to the foreign agent. But the replies from the mobile host to the foreign agent, to the correspondent node, go straight through the internet. So this path is very inefficient, the forwarding of the packets from the correspondent node to the home agent to the foreign agent. As an example, let's say I am sitting in France and the guy sitting next to me in the conference room in France is sending me a packet that has to go from France to Oklahoma, I don't know, 3,000, 4,000, 5,000 miles, and then it has to go back to the same place in France in the conference room. Although the two of us are just sitting 10 feet apart. So the routing path is very, very inefficient because it uses the forwarding mechanism. It also has a lot of conflict with the security solutions like ingress filtering and firewalls. And there are also issues like survivability and manageability. If the home agent dies, then you are out of luck. Not only you, all those mobile devices which depend on that home agent are out of luck, unless we have redundant home agents and all sorts of stuff. Now, some of you might be thinking that I am showing you these drawbacks, but there have been solutions to a lot of them, like the conflict with network security solutions. There have been solutions for making the routing path efficient. But what our experience is, when you apply these patches which were developed to solve these problems individually, and when you apply a lot of these patches, they don't work together very well because they were mostly developed to solve individual problems, not all the problems in one shot. So you might be applying a patch to make the routing efficient, but then as soon as you apply the patch also for the security solution and for latency other stuff, they don't work very well most of the time. So we started working with NASA because a lot of these NASA projects consider using IP in space. And here are some examples. This is a project called GPM. They measure the precipitations on Earth. There is another project called CANDAS. They are trying to demonstrate communication navigation in shuttles. There are projects to prove that the nodes, the operating missions can be used as nodes on the internet called Omni. So NASA has been working with Cisco to develop a mobile router because the router you are going to put on a satellite is going to be mobile. Mobile IP is very promising for a lot of NASA projects. And here are some of them: the A2, T2 project, the WINCOM project, small aircraft project. Actually, a lot of projects which, a lot of these projects are going to benefit if you can connect those devices to the internet. I mean, if we look at our cell phone, at one time, our cell phone only used to be able to talk and send text. But as soon as we connected the cell phone to the internet, we got the smartphone. And look at the smartphone, it has replaced tens of devices we are used to have. It has replaced the camera, it has replaced the GPS, it has replaced the timers, it has replaced MP3 players, it replaced everything. Even it replaced the land phone nowadays. I mean, nowadays, if you go to places like China, they don't even use the cell phone carrier, or they all use all the internet protocols to talk to each other. So as soon as you connect anything to the internet, it gives you endless possibilities of developing applications. And that is a big advantage of connecting anything to the internet. So our objective is to develop very efficient, secure, and seamless handoff scheme, which would be applicable to both satellites and wireless cellular environments. At this point, I should say that at one time, these mission agencies like NASA or DoD, they have tons of money. Whenever they needed to develop something for their missions, be it NASA or be it DoD, they used to develop it from scratch, and they had their own solutions. But nowadays, money is tight. So these mission agencies nowadays started looking at what solutions exist, and can we take those solutions and modify it to our needs. And as a result, NASA started looking at mobile IP, whether they can use mobile IP for mobility management in space. Because there has been a lot of investment in mobile IP. There has been a standard from IETF. So they started looking at mobile IP. So we spoke to them saying that see, mobile IP is fine, but there are lots of issues with mobile IP, the sort of issues I mentioned in the previous slide. So we said that while you are experimenting with mobile IP to do mobility management in space, fantastic, go ahead and do it. In parallel, why don't you develop another protocol from ground up, which will be very efficient, which will not have all these issues which mobile IP has, or the base mobile IP has. For example, our new scheme will not need any new hardware. That is one big advantage of the scheme we're developing, or we developed actually, that no new hardware or software components need to be installed in the internet infrastructure, which means that implementing it is much easier because you don't have to work with the ISPs. The handoff latency should be very low, and packet loss rate should not be perceivable to the user. There might be some loss, but the user should not be able to see that loss. The important thing is data path should be very efficient. We should avoid triangular routing, which we find in mobile IP. It should work with the security mechanisms which are already there. It should have good survivability, scalability, and manageability. And of course, it should be suitable for satellite networks and also terrestrial networks. Because when you invest a lot of money to develop a scheme, you will find that mission agencies sometimes give them for use by general people, like because they're all developed by taxpayers' money. Two of the biggest examples I can think of is one of them is a GPS. It was developed by the DoD, and nowadays everybody can use it and see how much we use the GPS. I mean, it's hard to imagine our life without GPS. We use the GPS everywhere. Second example is the development of the internet. That was also developed by the DoD, Department of Defense. And then nowadays is used by everybody. I mean, I don't have to tell you how useful the internet is. So whenever we develop something for the mission agencies, one of the objectives should be to develop it in a way so that later on it can be used by the general public. So we developed this protocol called Sigma, which has the same objectives of mobile IP. That means doing mobility management in space, but it doesn't have those 5 or 6 disadvantages that mobile IP has, because we developed this from ground up. So we looked at mobile IP. Where are those issues coming from? What can we do to fix those issues when we're developing the new protocol? And we found that the location management, that means being able to locate a mobile device, and the handoff, which is the reconnection from one access point to another access point when the device is moving, they are actually coupled together in mobile IP. And that gave rise to a lot of those 5 or 6 issues I was showing you. So our first objective was to decouple the location management from the handoff. That is our first objective in order to solve those problems. Not only that, we wanted to carry out those 2 operations of location management and handoff in parallel to data transmission. And the other thing is mobile IP is basically packet forwarding and sits at the network layer. The throughput of a system is based not on the network layer, is based on the transport layer. That is the layer which tries to optimize the performance, the throughput of data communication. So we thought that if we can allow the transport layer to do the mobility management, then it can also be aware of the throughput. So we wanted to have the new protocol to sit in the transport layer. So while we wanted to implement this new protocol, we needed one thing which is called multi-homing. Multi-homing means a device has multiple IP addresses, and all those IP addresses can be used at the same time. And we came across this protocol. It's an IETF standard called the Stream Control Transmission Protocol. It's a transport layer protocol, just like TCP and UDP, but it has 2 advantages. One is the multi-homing, another is the multi-streaming. And I'm going to tell you about those very soon. So the basic concept of Sigma is very simple. If we look at mobile IP in detail, it is based on disconnecting from the old access point before reconnecting to the new access point. So first it disconnects, it breaks the connection before it makes a new connection. And due to this, there is a big delay in handoff and also packet loss. So when I teach this subject in my class, I usually tell them about this issue of breaking the connection before making a connection, and versus making a connection before breaking a connection to the students. And I give them the example of this job search and job switching, because that's when they wake up and say, oh, something about job related stuff, let's wake up. So I tell them that if you already have a job, which is you are connected to the old access point, and you want to get a new job, you don't resign from the old job or the current job before starting to search for the new job. You apply for the new job while you are in your current job. And when you get the new job, you resign, saying that Friday is going to be my last day. You resign, you finish off on Friday, and then Monday you start the new job. This allows you to get your paycheck continuously. If you had given up the job, resigned from the job, and then searched for the new job, then you might be out of luck and might be out of paycheck for weeks and months. You never know how much it is. So that's exactly what I tell them, that mobile IP is something like giving up the job and then starting to look for a new job. And I said, we are going to develop this protocol Sigma, which is the other way around. We're going to find a new access point, hand off to the new access point, communicate with the new access point and the old access point at the same time, concurrently. Then when the mobile device moves fully to the new access point and doesn't have any communication with the old access point, we terminate the old connection. It's like resigning from the current job. And this ensures that your data communication is continuous. That is what we wanted to do in Sigma. So the basic concept is make the connection before you break the connections. And the advantages obviously are the packet loss were reduced because we already have multiple connections at the same time. The handoff latency is not even perceivable by the user because we are having connections of the both simultaneous connections at the same time. The throughput is much increased because we have two connections at the same time. There's no special requirement on routers and access networks. The only problem is having a protocol which can communicate over two access points at the same time. And that's exactly what multi-homing is. So we found this protocol called HTTP, I just described in the previous slide, and it supports multiple IP addresses at the transport layer. And this has been a big help for us in developing the Sigma protocol. What we do is we have a connection through the network 1. Then we connect to a different network, which is network 2, which is a new network. We communicate over both connections. At one point, we disconnect from the old one. Now let's see what is HTTP. You might be thinking we're discovering something new. It's nothing new. It is there in the IETF standard, and it sits right over there in the transport layer along with TCP, UDP. And HTTP actually is a protocol which ships with the Linux. It ships with the Windows. The only thing is we don't use it because we don't need to use it. We are used to TCP and UDP. All our applications are running nicely over TCP and UDP. We don't need to use a new protocol, even if it is better. So one thing is internet is people don't use a new protocol unless they have to, unless there's a need, or money is to be made by using a new protocol. Someone will make the money. It may be the internet service provider, or someone has to make money. That's another case when we go over to new protocols. So the HTTP has two features over TCP. One thing I should say is it's a protocol which has all the features of TCP, like it's a reliable transport protocol, just like TCP. It has similar congestion control like TCP, like slow start, congestion avoidance, all those nice features of TCP. In addition to all those features of TCP, it has two new features. One is multi-homing, another is multi-streaming. Multi-homing I already described. Multi-streaming means you can stream multiple streams over one connection. I'll give an example of a web page loading. There might be 10 images at the same time. These 10 images could be sent over 10 different streams. So if packets are lost in one stream, the other streams will keep going, and you will see that one image has stopped updating, but the other 9 images are actually updating. So that's a big advantage. Of course, we are not using multi-streaming in our current research, but we're using the multi-homing one. So HTTP was originally designed to support SS7 signaling over the IP networks, and it supports most of the nice features of TCP. It's an IETF standard. As you can see, it's a reliable transport protocol, and so it's all the good features of TCP. So we are used to, in TCP world, we're used to the word called connection. We establish a connection between computer A and computer B. In this particular case, we have to get used to the word called association. So computer A is associated with computer B, and computer A has two interfaces. One might be to the Wi-Fi network, another one could be to the 5G network, and computer B similarly has interface to the Wi-Fi and the 5G. And there is association which is set up between the two computers, and both interfaces can be used to send data. if you look at our smartphone, we have Wi-Fi there, we have 5G there, but we are only limited to using one of them. We can't use both of them. I mean, I have paid for both of them. Why can't I use both of them? It's a limitation coming from the phenomena we have been used to, that we have to use one of them only. The TCP doesn't allow you to use both of them. So in this particular case, if we use SCTP, then we can use both the Wi-Fi network and the 5G network simultaneously to communicate with computer B. This gives us higher throughput. And I have shown only 2 networks, but you can connect as many networks as you want. So this computer A has one IP address from the Wi-Fi network, another IP address from the 5G network. If you have a third network, you can have a third IP address, and you can actually send data from computer A to computer B using all the 3 IP addresses. So that's a big advantage of multi-homing, which is supported by SCTP. Now let's look at the signaling, the sort of signaling that goes on in our protocol. So in the Sigma protocol we developed, we have this satellite which is connected to the ground station and being accessed by this person. So we are talking about internet protocols. All these internet are connected to the mobile devices. And as the device moves and gets a new IP address from a new ground station, it tells the user that I have a new IP address, and the user can actually communicate to the satellite devices using both IP addresses at the same time. And we are talking about the LEO satellites, which are continuously moving. At one point, the satellite has to update the location manager so that people can find the devices on the satellite. And this is very similar to when we are actually moving with our cell phones. There's a location manager which tells the network whether I am in Oklahoma, or whether I'm in Florida, or where I am. And as I move along, my phone continuously keeps on updating the location, my location. That's how the calls are actually rerouted to wherever I am. So those are the signaling procedures that go on in Sigma protocol, which we developed for NASA to manage the mobility management in satellite networks. One big advantage of this Sigma protocol is called vertical handoff, which is extremely difficult. Excuse me, extremely difficult to do with mobile IP. So here is an example. There's a user which has a mobile device, and when the person was inside the building, it was using the wireless LAN like Wi-Fi. As the person moves out of the building and goes outside of the building, it connects to the cellular network. Usually, most of the time, it's already connected to the cellular network. And it tells the correspondent node that I have I'm using a different network now, cellular network. So I've got 2 IP addresses, one from the Wi-Fi network, another one from the terrestrial network. And please send data over both the connections. So the user receives data over both the networks, and also sends data over both the networks. So throughput is even increased. So as the user moves further away from the building, it loses contact with the Wi-Fi network. Then it sends a message to the correspondent node that my Wi-Fi network is no more there. Do not use that IP address. Use only the IP address provided to me by the cell phone carrier. So after that, the communication is only over cellular network, because it's out of range of the Wi-Fi. As it moves out of the cellular network coverage, let's say it goes to a place where there's a forest, there's no cellular network coverage, it can hand off to the satellite network. So it establishes a connection with the satellite network, and at one point it loses communication with the cellular network. So it tells the correspondent node that please send all data through the satellite network. Basically, it says that this is my IP address where you should communicate with only. That is telling the correspondent node which network you should send the data to. And this is called vertical handoff. You cannot do this in mobile IP. It's almost very difficult, because you have to tell the operators of the cell phone network, you have to tell operators of the satellite network and the Wi-Fi network that I'm going to do this sort of stuff. And you have to have home agent and foreign agents all the places. It's extremely difficult. Here we demonstrated this using the Wi-Fi network and the Sprint network. And we did a seamless handoff from the Wi-Fi to the cellular network without telling the ISP, or without telling the cell phone operators, because as I mentioned earlier, our protocol works at the transport layer, which is at the edge of the network, which is on your device actually. So we do not need to even contact the network operators, because network operators can only work up to the network layer. They cannot even go to the transport layer. So this was a big demonstration and a very successful demonstration that we can do vertical handoffs between networks which are dissimilar, which have different protocols, without even telling the operators. So we developed an experimental testbed to start with to demonstrate the concept, and this was the mobile IP testbed. We're using the computer science network, and the correspondent node sends data to our university's computer science network, and we have a home agent and a foreign agent. We have an access point and the second access point. So we moved the device from one access point to another access point. So that is a very, very simple testbed, just to demonstrate the advantages of Sigma over mobile IP. Because the more complex the infrastructure is, the harder it is to explain why the improvements are happening. So this was the mobile IP testbed. And then we developed the Sigma testbed. For that, we used exactly the same hardware, same configuration. Everything was exactly the same, except that you can see there is no home agent, there is no foreign agent, because the Sigma protocol works at the transport layer in the node, in the mobile node, and in the correspondent node. And we did the handoff using Sigma and mobile IP. And we're using standard stuff like Linux operating systems, and we use network adapters, which are standard network adapters. We do not use anything special. These are standard adapters we used. Let me give you quickly some examples of how the performance happens. This is a mobile IP handoff, and this is time versus throughput. As you can see, we are moving the mobile device as time progresses. So when you move the mobile device, the throughput varies. And this variation in throughput is normal in any network because of TCP congestion control, because of other people using the network, all sorts of stuff. So this variation or this fluctuation in throughput is happening all the time without handoff even. But if you look at somewhere between 50 to or somewhere in between 40 to 60 seconds, that region where I put a red bar, you can see the throughput drop to 0. That is where the handoff took place in mobile IP. So we're talking about mobile IP now. So that's when the handoff took place. And clearly, there was no communication during that time. So I'm going to next show you the slide for the Sigma with exactly the same hardware. So if I tell you, if I don't show the red line and show you here is a throughput, where do you think the handoff took place? And you probably would guess, probably here around 140 seconds, 150 seconds, that's probably where the handoff took place. But we looked at the log and find out when the handoff took place. And I put a red bar to show that the handoff actually took place around just after 20 seconds, 22 seconds. And you can see the throughput has not dropped at all because of the handoff. And the reason is very clear. There's no magic there. There's no magic there because we connected to the secondary network, the second network, simultaneously with the first network. So when the handoff took place, it just was a seamless handoff from the first network to the second network. So this HTTP, the protocol we developed for the handoff, can do seamless handoff without the user even knowing that the handoff took place, without even telling the service providers that we want some special hardware to do handoff. Now, whenever we do a project with a mission agency like NASA or Department of Defense, they measure the maturity level or the readiness level using a measure called technology readiness level, and is used by all mission agencies. Because when you develop a protocol, you're going to deploy it in a real satellite. I mean, you can't go and reboot the device, and you can't go and apply a patch. Or if you have a new protocol which you are implementing in a tank, for example, these tanks are in the deserts everywhere, and you can't implement something which might fail. I mean, if it fails, then you are in big trouble. The enemy is there, and you are going to be in big trouble. So before implementing any protocol by the mission agencies, they follow this sort of technology maturation or technology readiness level thermometer to see how mature the technology is, how ready it is to be deployed in a real mission. We're not talking about something at home or something in our office where we can reboot, where we can change stuff, where we can apply patches, and if something breaks, we reboot, just like I rebooted my computer, so we delayed 5 minutes. This sort of thing cannot be tolerated in a real mission like a war, for example, in a desert or in a warfield or in an actual mission up in the sky. So the TRL-1 is the basic technology, basic principle. These are usually basic science like physics, chemistry people do. Then at TRL-3, we develop something and then we prove analytically with experimental experiments and simulations like stochastic modeling, or the analytical modeling stuff, or we do simulation using NS2 simulation for networks. And once we have demonstrated the what we have developed using these, we are still at TRL-3 only. We need to mature this technology further if you want to go to actually deploy the technology in a real mission. So the next thing is to, whatever you have developed, is to implement on a prototype in the lab. So you build a prototype in the lab, and a lot of us who are in networking, we develop these prototypes based on Linux machines and with Cisco routers and all sorts of stuff. And if you can show that it works, then you are at TRL-4. But again, this is not a real environment. So at TRL-5, if you want to reach TRL-5, you have to implement whatever you developed in the lab on a hardware which is in real operation, like whatever hardware is up in the sky, or whatever hardware is in the tank, the real tanks. So you have to get those hardware in the lab and demonstrate that your protocol, your technology works. Once you have done that, then you have to show that your technology works on the hardware, but not in your lab. Actually, it should be in real space, in the satellite, or in a real place like a war field in a desert. You have to show that it works, but not in a real war. But this is showing that it works in an environment. For example, if you can demonstrate that it works in a tank in a desert where there is a lot of vibration, where there is a lot of dust, where there is a high temperature, in a desert like the Middle East, there's high temperature, or it could be in a place where there is extremely low temperature, and it could be in a satellite environment where there's radiation, very little power, all sorts of real world environments you have to show, but still it is experimental. Then you have to, so then you have to go up the TRL, and actually you have to show that it works in it is flight proven, successful mission operations and all sorts of things. So what I'm trying to show is, or what I'm trying to say is, all the university stuff we do usually are at TRL-3, and this is good for students to graduate, doing some stochastic modeling, some simulation, for faculty to get promotion and tenure, all sorts of stuff. But a lot of these are extremely difficult to implement because of all this readiness level testing. And we're happy that in Sigma we went up to TRL-5 and 6, somewhere in between. We got the hardware from the satellite up in the sky in our lab, and or we had access to the satellite hardware in the lab, and we demonstrated that we can actually do it. So we went somewhere between 5 and 6, and after that, going to TRL-7, 8, 9 actually has to be real commitment that we really want to go to the mission with this new protocol, and it involves much more money because you have to work with the in the case of space, you have to work with the satellite companies. In the case of DoD, you have to work with the tank companies, or wherever you're trying to implement those. So this is the hardware we implemented. This is a solid state data recorder. Basically, it's a single board computer which runs, or which actually is implemented in the Surrey Satellite Technologies Limited. This is a company in Surrey, in England, Surrey Satellite Technologies Limited, and they've got a disaster monitoring constellation where there are a number of satellites in orbit, looking down in Earth, or down at Earth, looking at disasters. So NASA had a copy of this hardware in their lab, and with access to that, so we implemented our Sigma protocol in this particular hardware, when we wanted to implement our Sigma protocol in this hardware, we found that this hardware is based on PowerPC, which has very little power. It's based on operating system called RTEMS, which is very rudimentary, it doesn't even have the full network stack. Because when you are flying these single board computers up in the space, you don't need a USB driver, you don't need a monitor driver, you don't need a keyboard, you don't need all those gadgets we have in a standard computer. We have a laptop or a desktop. All it needs to do is collect data from the sensors and then send them down to Earth. So when we tried to develop this or implement this Sigma protocol up in this real hardware, we ran into lots of issues. The processor was not powerful enough. The operating system didn't have the ability to do sort of stuff. The memory was very, very, very limited. So our protocol did not even fit into the memory. And then we had to spend lots and lots of time to trim our protocol, to implement the networking protocol stack in the operating system. Lots and lots of things we had to do when we went to phase 5 or RTL 5 and RTL 6. So my advice is to all people who want to actually develop technology for a mission, that the mistake we made was we did not look at the actual hardware we are going to implement it on. And we used very sophisticated hardware like, Pentium machines, state-of-the-art Pentium machines. We used the state-of-the-art Linux operating system and everything worked fine in the lab. When we want to implement here in the sky, nothing works. So my advice to all those who want to do mission-oriented research is to look at the target hardware even before you think of how to implement your technology or how to develop your technology, I would say. So that is going to be a very critical component for global coverage. As you have seen nowadays, there are projects to beam the internet up from the sky down to Earth. So it's going to be a critical component for covering the whole world. There are many mobility issues which arise due to the movement of the satellites, and the main issue arises is because they are far away with error-prone links. So we need a very efficient mobility management scheme for satellites. And we developed this scheme called Sigma, which is developed from ground up without any issue or any of the disadvantages of mobile IP. So the other thing which I just mentioned is pay attention to the target system before you develop the protocols for systems which are actually mission critical. One thing I should mention is, in order to use the Sigma protocol, we need to recompile the applications. That is the only disadvantage we have over mobile IP, that you have to recompile the applications. But if you are implementing this in a mission like what we did for what we're doing for NASA, they have the source code for every application they have, number one. Number two, the mission usually doesn't use thousands of applications. The mission uses a few applications, and it's pretty easy to recompile those applications by replacing the TCP socket calls to HTTP socket calls. So if you are doing it for a mission, this Sigma protocol is extremely suitable for managing mobility in systems, in mission systems. There are a lot of people who have worked on this project directly. These are some of the main ones, and there are people from NASA, as you can see, William Ivancic, Wes Eddy, David Stewart, and I must acknowledge their help in guiding this project. Lloyd Wood from Cisco helped us. He was in the Cisco UK. And there are a lot of PhD students and postdocs and professors. And this project was funded by NASA, so I must NASA and Cisco. I must acknowledge their financial contributions and guidance. Thank you very much, and I'll be happy to answer any question you might have.
So at this point, we're going to open it up for questions. If you do have a question, you should see a reactions button in the bottom corner where you can raise your hand. And oh, sorry, I'm being reminded I need to turn my camera back on. So hang on just 1 second. So at this point, we're going to open it up to whoever, to any questions anyone might have. please raise your hand and it'll show up on my screen that you have a question to ask. You can find it in the section that says reactions, and then it should have an option that says raise hand. Daniel, if you're saying something, it's we're getting a lot of echo on that.
I'm speaking now. Can you hear me okay?
Yep, we can hear you now.
Dr. Atiquzzaman, is your project on GitHub, or how are you publicizing your project? Is my first question. And the second question is, beyond changing it from TCP calls to the protocol calls, how does the client software find the host that it wants to speak with? Under normal circumstances, we use DNS for that function. How is it performed in your design?
Okay, the first question is, we haven't released the code yet because the code contains some proprietary code as well, which we obtained from the Surrey Satellite Technology Limited. So we could not release the code for that purpose. But we have tons of publications where it tells you exactly how it works. We have analyzed the performance, we have analyzed the throughput, we have analyzed security solutions. Everything is there. All someone needs to do is code it. There's not too much of code. It's mainly the handoff code. And if someone is really interested in implementing a commercial system or really wanted to implement an emission system, we can always remove the proprietary code and then help you with that code. That is possible. The second thing is finding the host which you want to communicate with. I mean, you do it normally. Here, there is no difference between how you do it normally. And in this one, only thing we have done is change the call from TCP to HTTP. That's all. Nothing else changes. Everything remains the same.
Well, no, I understand the part with the TCP, the IP communication, but still, how do you, if the host is moving around, in other words, it's in low Earth orbit, and it's constantly changing its IP addresses, how do you establish the first communication with that host if you can't use DNS because it's updating its IP addresses so frequently and has multiple IP addresses?
Okay. We use the location manager actually. So we have a location manager, and we use the DNS actually. In fact, so whenever my IP address changes, I update the DNS, and you can actually update the DNS very easily. And actually, this is done by big companies like Yahoo and Google and all these people. When you access google.com, they will change the DNS so that you are redirected to a different server. So they do it for load balancing. So this is not a new thing. People have been doing it all the time.
Okay, thank you very much. Excellent presentation.
Thanks. Thank you very much.
Okay, do we have any additional questions?
I think I can see one in the chat saying that, what about the performance of Sigma, latency? Latency is almost zero as perceivable by the user. The reason is you're just communicating over standard networks. So the latency, there is no extra latency in Sigma over what you would have with TCP. And the latency coming in mobile IP is because of the forwarding. Here we don't have forwarding, we have direct communication, and there is no extra latency involved due to the use of Sigma. Performance, as I showed you, that the throughput is way better than mobile IP because we can communicate over both channels at the same time, multiple channels at the same time. So the performance is much better than what you would get in mobile IP, where you would be communicating over one connection only. Is it compatible with IPv6? Yes, we don't specify any protocol like IPv4 or v6. You can use any one of them. We just do the hard handoff using the transport layer. So IPv6 is at the network layer. We don't even do anything with the network layer. We just do everything with the transport layer. So the next question is, won't the system for LEO still require many ground stations for interconnectivity to the satellite, similar to the cell phone system? Yes, that's a very important thing that we need to fully utilize the capability of this system, we would need ground stations which are overlapping in coverage, which is not still there, but soon there would be a lot of ground stations. And sometimes you don't need a ground station. We developed a scheme which I did not show you here. If you do not have a communication with the ground station, you can communicate with another satellite via intersatellite links. And as soon as you communicate via intersatellite links, you can think of the satellites up in the sky as a web of satellites. They're all interconnected to each other. And that is what you will see very soon, because all these small sats and CubeSats coming in, there will be thousands of them. They'll all be connected together. So if you want to connect to a ground station, you can always connect to another satellite which is within your reach, and you can hop from satellite to satellite until you reach one which is connected to the ground station. So if you're not in contact with the ground station, it's no big deal. If you have connection with other satellites. Do you know what protocols are used by commercial systems like SpaceX, Starlink? I'm sorry, I don't have much idea about those because they're very proprietary, and I've tried looking at those, but I couldn't get much information about those protocols. Alvin Chin says, actually, Alvin, probably we have met before. I remember meeting you before. So Alvin asks, how do you handle power management for these devices if one is running on the low power and you may need to hand off so you don't disrupt the connection? The power management for these devices is done by a lot of the time shutting off the interfaces when there is not much communication going on. So we implemented those schemes where these interfaces are put to sleep whenever they're not communicating. So those things are taken care of by those modules. Peng is asking, could I ask how the encryption is handled around SCTP? In this project, we didn't worry about encryption because we use the standard encryption, what you would use in any system. Encryption is not an issue here because we are only doing mobility management. Whatever encryption you want to use at the application layer, go ahead and do it. Then Fabian is asking, would using network edge on the ground be a way to access connections to further the ability to hand off to moving connections? Yeah, we have actually implemented our scheme on network mobility as well. We extend the scheme where you're not handing off only a device, you're handing off a network. That is exactly what happens when you're flying in an aircraft. Let's say you're on a flight and you're connecting to the local onboard Wi-Fi network. That flight, that aircraft has a mobile router which is connecting to the satellite, and that router's connection is handed off between satellites. It's not your connection. So we implemented our Sigma protocol on a mobile router so that the router can hand off between satellites and the devices are unaware of what is going on. That is actually the architecture which will be there if you implement Sigma on a satellite, because the satellite will have an onboard LAN which will hand off between ground stations instead of the devices, instead of scientific instruments we're talking about. What about the security aspects of Sigma? This is a transport layer SCTP thing we're doing. So we don't introduce a new security aspect here. All we do is, instead of calling the TCP sockets, we call the SCTP sockets. And if SCTP sockets are secure, then there is no additional security loophole which has been introduced because of Sigma.
I just want to, so I'm going to go ahead and ask if there are any other questions. Please either raise your hand or send it by chat. Looks like we have a question from Pang.
What is the GS elevation angle that has been tested or experimented with testbed? We actually haven't tested it in real flight. As I said, that is PRL 6 or 7. We haven't reached that point. So we're basically testing our scheme on a real satellite hardware from Surrey Satellite Technologies Limited, but in the lab. So we didn't do it in the in flight. If you wanted to implement this in an experimental flight, that would require a lot of resources in the sense that we have to work with the Surrey Satellite Technologies Limited, and also it has to be really someone who wants to do it in mission has to decide that, yeah, we are going ahead with that before we invest into money to test the TRL 7, 8, 9. Those are the most expensive ones, testing the TRL 7, 8, and 9.
Okay, so to answer Fabian's question, as long as Dr. Atiquzzaman does not have any objections to it, the plan is to make this recording available.
Sure, I have no problem. As a university, our policy is philosophy is to broadcast knowledge, not hide stuff. So please go ahead and distribute to anyone you want.
Perfect. Looks like Alvin has another question for you.
What about the security and reliability of the network if one of the devices may be compromised? See, it would be the same security as you would have. Let's say you are having a laptop which is using a Sigma. If that security of the laptop is broken, or the reliability of the network is broken, then you do something, and you do the same thing here as well, here also, because we're not doing anything at the application layer. We are doing everything at the transport layer, and at the transport layer, whatever security we have, we're going to use it. So to answer your question, Alvin, whatever security we would use normally, we'd use that security in Sigma also. Because the applications are exactly the same, there's no difference in applications. Yes, Ken has a nice question saying that you can simulate flight to some extent by using delay device that can also introduce loss, etc. Yes, we can do that. We did that actually. We introduced the software to introduce delays and all sorts of error losses and all those stuff we did. But those are all simulation stuff. Those are at level TRL 3. When we are going to TRL 5 and 6 and 7, we have to really work with the real hardware. But you are right, Ken. We did that already at TRL 3. So Chris has a question. Given that most NICs pass off processing to the CPU, how much performance impact do you see per extra multi-homing stream? And what is the upper cap where you would see a performance impact? Honestly speaking, Chris, we haven't looked at this issue. We didn't even think of this issue. But since you raised it, might be in our next study, we're going to look at this issue. We haven't looked at it, in fact. And especially, Chris, I should say that what you mentioned is very important, because when you implement Sigma on a satellite, and the one I showed you, the single solid state single board computer, which has PowerPC and a very rudimentary operating system, and it really might affect the system, our system, because running 2-3 different interfaces might produce a load on that PowerPC, which doesn't have power left anyway to implement our protocol even. So Fabian, you are asking, I didn't know they do that actually. Which one? What do you mean by do that? What are you referring to? Oh, the NIC. Okay. Yeah, I also did not know that, but that's a good point to investigate. And that would be a problem in a satellite environment. So one thing we discovered is the missions, like the satellite missions and the DoD missions, and any mission uses very simple hardware, very well tested, very old hardware, because they have been well tested and they work. So that's one eye-opening thing we had, that these missions don't use state-of-the-art hardware and state-of-the-art software and state-of-the-art operating system we are used to on our desktops and laptops and at homes, because they want something which works without fail. So it has to be heavily tested and very simple, because we don't need complex stuff in mission. In a mission environment, those hardware just do one or two or three few things. It's not a general purpose system. Like our laptop is a general purpose, our desktop is a general purpose, smartphone is a general purpose thing. It has to do everything. But those mission computers only do one thing or two things, but very reliably, very stable, and very well.
Okay. I think we've reached the end of it looks like we've reached the end of the questions for tonight. Thank you for your time tonight. It was definitely very informative, and for those of you that are still on the Zoom meeting, this will not be the last one that I organize. We had 50 some odd chapters that co-hosted this one, and I'm going to probably look at setting up another one with one of the distinguished lecturers sometime into the spring. Again, Dr. Atiquzzaman, thank you for your time tonight, and I look forward to working with the other chapter chairs that are on the call tonight to continue making sure that these virtual lectures are available to the widest possible audience.
Michael, thank you very much for hosting this and inviting me, and I sincerely thank everyone for attending. I can see a very, very good attendance, especially at this time of the day when everybody is having dinners. Thank you again for coming.
All right, so with that, we'll conclude this for tonight. If you have any questions, please feel free to send an email at the contact information provided. And we will look to see. So Chris, to your point, we will be looking to share this as a video recording. I got to work out how exactly I'm going to do that, and as soon as I do that, I will make sure that that goes out to the folks that registered for the meeting. Yes, absolutely. We will be emailing the presentation, and well, we will be emailing a link to the presentation or video, because typically these videos are hundreds of megs. So I don't know that sending them by email, the actual video by email would probably not be a good idea. Okay. So we will, so I will sort out how we get this on YouTube, and we'll get this, we'll get the link sent out just as soon as we have it posted somewhere. Thank you everyone for your time tonight. Have a good night.
Thanks. Bye-bye.